Okay, so let's start with uniform flow. Now, uniform flow, we're all used to it, is basically the horizontal flow in one direction at a velocity capital U. We all know that. So that's kind of the basic flow that we all know. It's basically like free stream flow, sorry. So we all know what free stream flow is. So remember, we're trying to focus on 2D in the XY plane. And I have a flow, uniform flow of a speed capital U coming from left to right. Okay? So really the streamlines are along the flow lines here. So the blue lines here obviously are the streamlines, nice and horizontal. And I told you last time that along a streamline, the stream function psi is actually constant. Okay? So if I take this streamline, then you get a constant phi for that. If we wanted to plot the phi's, not the psi's, we told you that they are at 90 degrees to psi's. So all you need to do is just plot lines that are perpendicular to psi, and that would be your velocity potential function. All right? So we have a 2D space. So the velocity has a u component and a v component, little u, little v. Can anyone tell me what u here is? By just looking at the flow, what's u, little u, equals to? Okay, let's put it this way. Is there a vertical velocity component? Yes or no? No? Yeah? So the little v is 0. Is everyone happy? Yeah, because the flow is absolutely horizontal. There's no flow in the vertical direction. That's good. So the little v is 0. How about u? What do you think u will be equal to? Huh? Capital U. Very good. Yeah, that's it. So the basic form, horizontal flow, the velocity component, little u, is the same as the uniform flow itself, and there is no flow in the y direction, so little v is 0. So how then do we get forms? So the next question is, how does the stream function and the velocity potential look like? Well, to do that, you guys need to recall these equations we had last time. So this just relates the velocity component u to phi and v to phi in this formulation, or u from psi in this formulation. This here is basically the polar coordinates. So if I go from the Cartesian to polar, then x becomes r cosine theta and y is r sine theta. So I'll just show you very quickly. If you remember that u is capital U, v is 0. Let's get phi and psi. So let me do that very quickly on the. It's not very zoomed. Okay. So we said we have a uniform flow like that, okay, of speed u, and we know that little u is capital U, v is 0, right? So what we want is to find a simple equation for psi and phi. Well, let's start with the phi, for example. So we know that u is, anyone? d phi dx, very good. So that just means d phi equals u dx, right? Just by splitting the variables. Now, all I want you to think now, don't worry about the partial derivative. That's just the same as a normal derivative. So you can think about it at d phi equal u dx, right? It's exactly the same. So now all we need to do, we know, by the way, that u is capital U. So I can say that. All we need to do now, obviously, integrate both sides. So you got the integral of d phi equals the integral of u dx. And of course, u is constant. I can take it out, and it just becomes the integral of dx. Very simple. Hope you guys can see that. And as I said, just treat the partial derivative as a normal derivative. So think of that as dx. So what's the integral of d phi from 0 to phi, for example? What's that? What's the integral of d phi? It's the integral of dx. Why? Come on, guys, I'm trying to get some interaction. What's the integral of d phi? Huh? Phi, yeah, of course. What? Don't be scared, guys, okay. What's the integral of dx? X, very good, that's it. So that's how you get the equation for phi, very simple. And it all starts from this definition. Okay, let's get the equation for psi, for example. Okay. So for psi, we can use, we have also that u is d psi, anyone? D psi d y, yeah. So we do the same, so d psi is u times dy, which is basically u dy, and you can see by integrating, I can get psi, I'm not going to do it again, it's just u times y. Okay, so that's it, that's how you get psi, very simple, you can get it. So if I just come back, now I'll just show you the equations, of course, for psi and phi, that's how you do them. That's in Cartesian coordinates. If you want to use it in polar coordinates, all you need to do really, substitute the y here with r sine theta and the x with r cosine theta. So I'm going to do, and that will give you the equations in polar coordinates. Very simple. We can also get the complex potential, which can be shown to be u times z. Okay. I'll leave that to you as simple exercise. If you get stuck, ask me. Okay, so that's it really. Uniform flow, the basic form is the flow flowing horizontally left to right like that. But uniform flow doesn't have to be flowing horizontally, it can be actually at an angle. So we can do exactly the same in the general case where there is an angle and it looks something like that. So I have my uniform flow coming. The only difference now is at an angle alpha. Okay? You can think of that alpha similar to an angle of attack, but I'm not saying it's the angle of attack, but similar to that. But it's coming at an angle alpha. Okay, can anyone tell me, in this case, just from geometry and the vectors, what is the component u in this case in terms of capital U? Any guesses? So you can resolve u in the x and y components. Any guesses? So what would be the little u? Very good. And v? U sine alpha. Very good. And of course, when you think about it, okay, let me just show you that. So the little u now is u cosine alpha, v is u sine alpha. And of course, if we come back here, what should the alpha be? To come back to this, what should be the alpha? 0. Very good. So let's just double check. Cosine of 0 is 1, so that will give us u equal to u. That's correct. Sine of 0 is 0. That gives us v equal to 0. Which is exactly this case. So this is kind of a specific case for alpha equal to 0. We do exactly the same. If I do the same integral, treating alpha as constant, u capital as constant, you can show that equations for psi and phi are given that way, and the complex potential w can be written that way. So I don't think there's any need for me to have to go. Try to do it yourself. If you get stuck, let me know. It shouldn't be difficult. And again, to specify that the streamlines here, which are the blue lines, where we specify constant psi, okay, they are perpendicular to phi. Okay, so phi and psi always perpendicular. So if you know one of them, sometimes, not always, you can get the other one by just plotting it perpendicular to that. So that's it. That's the uniform flow. So that's the first building block. So let's talk about the next building block, which is sources and sinks. Sources and sinks. Right. So what is a source? Now, I want you to think about source as a very extremely short and extremely thin pipe, okay? Which in the mathematical sense it just goes down to a very, very simple thing like a point, okay? So it's an extremely short and extremely thin pipe. And out of that pipe, fluid comes out, okay? But it comes out radially outward on a plane, let's say the XY plane. but the flow is not rotating. It just comes out and it moves in radial lines like that. There's no rotation, because remember, we said this is potential flow. So in this case, the streamlines will be straight rays pointing outward from the origin, something like that. So the source, my source is here, this point here. And just imagine is an extremely thin, an extremely short pipe. And we know what pipe does. It gives you, for example, water. So, but the flow is coming radially outwards of that. So it's a very specific concept. It's radially outwards in all directions like that. So the blue lines again are the streamlines. This is how the flow is coming out. And to make things easy, we're going to use the polar coordinates rather than Cartesian. It just makes things easier. You can use Cartesian, it's not a problem. But we're going to use polar coordinates, meaning I'm going to use theta and r in my definition. So the streamlines come out, and the speed of the flow is called VR. So, and it's actually, because the flow is only going radially outwards, it will have a speed. But can anyone guess, is there any tangential flow? Is there any tangential flow, you think, or not? And why? Why is that, James? It's correct, but why? So the flow is coming radially outwards. So the velocity, there is a speed VR. So is there a tangential flow to that or not? It's true. Very good, yeah. Because the flow is only radially outward. There's no flow in the tangential direction. There's no flow in the theta direction, if you like. It's only along r. Okay, so that's the first thing you guys need to notice. And this is why I'm using, so I'm using VR, the velocity radial, and theta, that's the tangential velocity, or some people call it circumferential velocity. It's basically the velocity along a circle, tangential to the circle. Right, and it's 0 because there is no flow going around. It's all radially outwards. I hope that's clear. So VR is non-zero, but V theta is 0. So remember, we're using the polar coordinates. So instead of little u and little v, we're using VR and V theta. So it turns out that the radial speed VR can be written as m divided by 2 pi r, where m actually here turns out to be the volume flow rate per unit length. So how much volume is going out at a given location r per unit length. Divide that by 2 pi r, that will give you the speed VR at a given location r. So what you guys notice is VR is clearly a function of r. So what do you think happens when r goes big? So what happens to VR? Becomes smaller, and vice versa. As r gets smaller, the VR increases. Okay, so very close. So as we come closer to the source, the speed is very high. As we go away, it comes down. So that's the first thing. It's a function. It's basically a constant divided by r, if you like, because m is a constant at a given r, and 2 pi is just a constant. So you can read it as a constant divided by r. Right. Don't get scared, guys. This is just the velocity components in polar coordinates. Okay, so again, instead of little u and little v, I'm using VR, the radial velocity, and V theta, the circumferential velocity. And if you look at previous notes, they can be shown to be written in this form. Okay, so again, they're functions of phi and psi like that. And we're going to use that to find equations, as we did before, for phi and psi. Right, so the stream function could be shown to be psi equal m over 2 pi theta. Right, let's do that. Let me just do that very quickly. Just another integral. So we have, so the radial speed VR is m over 2 pi r. Okay, and I have VR is 1 over r d psi d theta. Okay, so can we get an equation for psi? Of course we can. So all we need to do now is substitute for VR with m over 2 pi r. So you can say 2 pi r, m over 2 pi r equals 1 over r d psi d theta. Okay. What's the first thing we can cancel out? The r's, yeah. So the r goes, don't need it. So we have m over 2 pi equals d psi d theta. Right, so again we do exactly like before. Leave the phi on one side, get the theta to the other side. So what we can say is d psi equals m over 2 pi times d theta. Now m is a constant, that's just the flow rate at a given r. 2 pi is a constant. So when I integrate d psi, I can just leave this outside and just integrate with respect to the theta. Again, the integral of d psi is just psi equals m over 2 pi. The integral of d theta, let's say from 0 to theta, is just theta. Okay? So that's the equation for psi. We can do the same for how to get the phi. So, right, what we have is VR is d phi of dr. So really just integrate. That means, and it's of course VR is m 2 pi r. So that means d phi is, okay, what do I have? M over 2 pi r times dr, right? Integrate. I can leave the m over 2 pi outside, but I can't take the r, of course. So the integral would be something like that. What's the integral of dr by r? What's the integral of dx by x? Log, yeah? So that would be phi. So that's the integral is phi m over 2 pi, and that's just the log of r. Okay, that's how it is. You get phi. So if you know your maths, is actually not difficult. So that's just quickly to show you. We didn't just get those equations. We just integrated using the important thing is you have to use these definitions, of course. Now, okay, so we have this speed, the radial speed, as a function of r. Okay, and I think we said as r goes down, the VR will increase. But there is one very specific case, and that is when r goes to 0, i.e., when we come to the center of the source itself. Okay, which, by the way, here you might have noticed we placed it at the origin itself, where it's 0. So when r goes to 0, what do you guys think happened to VR from this equation? What happens to VR? Anyone? When r goes to 0? What? No. When r goes to 0, what happens to VR? 0. Who said that? Tends to infinity, yes. So it blows up, right? 1 over something goes to 0, it obviously goes to infinity. So if we go back to if we go towards r equal to 0, okay, then the speed will go to infinity, okay? Now, is that something real? Do you think, is there anywhere where speed can go infinity in real life? Yes or no? No? So that's not physical, is it? In mathematics, we just call that singularity. So singularity is usually where either something is equal to 0 or something goes to infinity, which is not physical, okay? So the speed is unbounded at the source, infinity. What is infinity? Okay, we can't have infinity. So this is a singularity. So that's the first thing to notice. Okay. Now this is source. A sink, you'll be pleased to know, is just the opposite to a source. So instead of the flow going outwards, what do you guys think happened with the source? Sink. Radially inwards. Very good. So just think about it like a small black hole for fluids, where it's just sucking everything in, but it's radially inwards. And all we need to do, honestly, just put a minus sign for all the equations we have seen. Okay? So VR will be minus m over 2 pi r, and put the minuses in front of psi and phi, and that's your sink. So if you understand the source, sink is just exact opposite to a source. So obviously I won't go through that. So these are obviously the psi and phi for a sink. Now, I think I have a final point here to notice. That's just the complex potential. Don't worry about it. I'm just adding it for information. So, and I'm putting plus and minus. Any guesses why I'm putting plus and minus? Why did I put plus and minus? Plus and minus, why? Very good, yeah. One is a source and one is a sink. Yeah, the plus is for the source and the minus is for a sink. So well done. So, and you can remember it this way. Right, that's sources and sinks. Let's go to the third building block, which is actually vortex flow. Okay, but before I show you the vortex flow, let me just have a little discussion about vortex flow itself before showing you the streamlines and stuff. Okay, so by definition, any flow pattern, okay, for which the streamlines are circular, okay, around a certain center, okay, a central point is called a vortex flow. So whenever, if you go to the wind tunnel and do some experiment, and you have a certain system to visualize the flow, and you will see something rotating, okay, in the circular flow, that's a vortex flow. So in general, that's what's vortex. So there are circular streamlines about a certain central point. Now, in fluid mechanics, there are usually two types of vortex flow. The first one is called free or irrotational vortex. So that means, okay, what do we mean? What do you guys think, according to what I've been saying so far? What do you think is an irrotational vortex flow in terms of fluid particles? What did we say about the fluid particles in an irrotational flow? Do they rotate or not? They don't. Very good. So they just move around. So imagine they're going in a circle. They move in a circle, but themselves, they're not rotating. They just translate along the surface. I guess think about it. You know, you've all been around, you know, those, central parks where you go into the wheel. Yeah, that's exactly. Imagine yourself with your mates as a block of fluid elements. You're not rotating as you go around, luckily. Otherwise, it's too much. You just go around in a circle, right? So that's an irrotational case because you're not rotating. You're just going around in a circle. So it's very important to remember that specific definition. So, so we have irrotational vortex or a force vortex. And the force vortex is something where the fluid elements may actually rotate. So, okay. So that's just repeating what I've said. Right. In a more physical sense, more scientific sense, a free or irrotational vortex doesn't require any external torque. Because remember, to create rotation, you have to apply a torque. Okay. So in free irrotation, we don't need any external torque to rotate the fluid mass, okay? But with the other one, the force vortex, we will need some external torque to do that. And the fluid elements will have rotation. Now, the other difference, you will see very shortly that in terms of, now the flow, remember the flow is going around in circles. Okay, not radially outwards, it's actually going this way now. So in this case, we don't have any radial flow. So VR, we had with the source and sinks, is actually 0. We only have flow around in circle, or the circumferential velocity. In this case, is v theta, which is non-zero. If the vortex is a free vortex, or irrotational vortex, it is found that the tangential velocity v theta equals roughly to some constant divided by r. That's how it varies. Which, as you guys can see, as r becomes huge, then what happens to v theta obviously again becomes 0, or it reduces. And if r is very small, v theta grows. So how does the situation look for a forced vortex? Just to let you know that for forced vortex, the speed v theta is roughly equals to some r multiplied by omega, where omega is the rotational speed of the fluid elements because they are rotational. They have some rotational speed. So it's a function of, so it's a linear function of r. The first one is constant divided by r. And this is another way of recognizing what's an irrotational vortex flow and a rotational vortex flow. So they both share the fact that they both go in circles, so it's a circular motion, but one of them, the fluid elements rotate as they go around, that's rotational, or forced vortex. The other one, they just go around and translate in a circle, that's the irrotational. And of course, that's the one we want to be concerned with, the irrotational, because we're talking about potential flow, which is, of course, irrotational. So graphically, just repeating what I've said, so this is an irrotational vortex flow where the circumferential or tangential speed, v theta, varies as roughly 1 over r, or a constant over r. And you guys can see here, when r goes to 0, again, the tangential speed blows up to infinity. So that's not physical. So very close to the origin, we have singularity as well. Examples of irrotational flows, things like tornado, maybe a bat flow as the flow goes from the going down, and wingtip vortices from aircraft. Now all can be explained by an irrotational vortex flow. In the forced vortex flow, the only difference here, v theta is linear to r, more specifically omega times r. Again, as r goes to 0, then the speed itself becomes 0. That's also a singularity, because singularity is either 0 or infinity. Okay, and an example of a forced vortex, things like the atmosphere itself, the mass of the atmosphere as it rotates around. Okay, so obviously there must have been an external torque to rotate that mass of flow, a huge mass of flow, to create a rotational flow. So these are the ways to characterize a rotational vortex flow and the rotational vortex flow. So as you guys can see, they're both going in circles. One of them is rotational, one is not. So I think I've shown you this picture before. Okay. So they're both vortex flows, isn't it? Because they're going in, the flow streamlines are circular. So that's by definition what a vortex flow is. But one of them is irrotational. That's the red kind of fluid particles. The blue ones are actually rotational. And if you actually look very carefully, you will see that the red ones, they just go in circles. They just slide along the circular lines. Okay. And if you can imagine there is an axis associated with them, those, as I said last time, those white lines, they don't move around. Okay, so but here there is a bit of a twisting. If you look very carefully, the blue elements are actually twisting, and we can say that we can watch that from the white lines. I hope you can see that. So this is a rotational flow. This is irrotational. Now, if you think about something like a tornado. So they've been talking about tornadoes. What is it? Something like an England match has been suspended. What's that? Joe? It's a rugby, Joe. You need to know. You're not following. Okay. Sorry, who said that?
The rugby game was suspended because of the typhoon.
So where is the rugby game?
Japan.
Okay. All right. So let's imagine there is a tornado like this. So very close to the center of the tornado, okay, you will find that the flow is rotational. So at the core, the flow is rotational. Outside is irrotational. So we can apply potential flow theory to understand the whole thing outside the core. Inside the core is rotational, so potential flow doesn't apply. Okay, but we can study outside. And of course, from outside, there is still a lot of effects of that tornado. So if we model that using potential flow, then we can know something about tornadoes. Right. So this is just tip vortices from aircraft. So that's another example of an irrotational flow. So you can actually get pictures like this if you use potential flow code or you develop a code for yourself or a software. You can get roughly something like that. Okay, so now I explain to you there are two types of vortex flows, and we're going to focus on the irrotational type, of course, because that's the potential part. So again, we have the flow picture here. So circular streamlines. The speed is only in the tangential direction. Okay, so v theta. There is no VR. VR is 0. And again, we are using the polar coordinates theta and r. So the blue circles are the streamlines, and therefore they are the same as the psi. Okay, a constant psi. Remember, streamlines are lines of constant psi. And if you draw lines perpendicular to these circular lines, that will give you the phi, because they're always 90 degrees. And of course, in this case, it just turns out that the lines of phi, constant phi, they're just in the radial direction, of course. Okay, so in terms of velocity component, I told you already that the tangential speed v theta varies as a constant divided by r, or roughly 1 over r. So there is no radial speed, of course. And from that, I should probably put it the other way around. And from this definition, we can actually get equations for psi and phi. Just do exactly what I showed you before. You just integrate, okay? Start from the definition, integrate. You definitely get psi this way and phi this way. Right, how is this related to circulation? Okay, let me just remind you what circulation is, because that's an interesting concept. And then how this applies to a vortex flow. So we need to find that circulation is equal to 2 pi k. Right, let me try to do that. So it's a vortex flow. So the streamlines are circular. So that's what we need to start with. So it's a circular streamline. And it's a circle, let's say, of radius r, like this. And of course, we have the speed is tangential, isn't it? We only have the tangential speed. There's no radial speed. Okay. And let's consider a small element like this. Okay. And let's call this small element, let's say dr. Okay. Let's call it dr. The speed, of course, at this very small element will be tangential. That's v theta. Everyone happy? Okay. And let's say this is at an angle theta like that. So, if you guys remember from maths, anyone tells me what the equation for dr, well, maybe that's dr is fine. What's the, how can I approximate this very small length of the circle dr in terms of r and theta? Sorry, that's a small angle, not the theta itself. This is a small angle theta, as a small angle d theta. Any guesses? R d theta? Yeah, d theta, because it's a very small one. R theta is fine, but it's a very small d theta here. Okay. And v theta is, of course, tangential to that. Now, circulation, what I told you last time, circulation, capital gamma, is if you go, is basically the line integral around a closed loop. In this case, it's true, because the vortex flow is a circular, closed line, of the velocity v theta times ds, if you guys remember. The dot product, or just multiplication there. Okay, all we need to do now is substitute. Okay, so what's v theta? It's k over r. That's just a constant divided by times ds, which is the same as dr here, which is r d theta. Okay. Okay, what happens here? What can we do? Cancel the r's, I think. Yeah? Everyone happy? So k d theta. So now how I have an integral in terms of d theta. Let me just ask you a very simple question. This is, of course, we're integrating around the circle. What do you guys think should be the limits of the integral if you go around the circle in terms of theta? 0 to 2 pi, very good. So I can just write this as the integral from 0 to 2 pi, because I'm integrating with respect to theta, and it's a circle, goes from 0 to 2 pi of k d theta. And of course, that will just give you theta from 2 pi to, and that's just k theta. Therefore, my circulation in a vortex flow is k theta. 2 pi. What happened to the 2 pi here? Sorry. Because I went already from 0 to 2 pi. Apologies. So it's k 2 pi. Okay? But k, what we have is that k, what we have is v theta is k over r. So we just substitute for, why am I confused now? 1 second. V theta is k over r, that's fine. That's fine, yeah. Circulation is 2 pi k, that's fine. Not sure I was thinking too much about it. And that's that's why, how they related. So v theta, therefore, can be, before, remember guys, it was in terms of k, but k itself is the circulation divided by 2 pi. Just substitute for that, you get the tangential velocity is circulation divided by 2 pi r. Okay? Now, remember I told you, if you go close, very close to the center of the vortex flow, then the speed goes to infinity, and we have a singularity at the origin. And if you actually take the circulation integral around a circular streamline very close to the origin, you actually end up with a non-zero circulation close to the origin. Okay? So, if you guys remember, the physical meaning of circulation is the integral of vorticity over a plane. Okay? So if you integrate circulation and it's non-zero, that means there is vorticity. Right? So now, close to the origin, we find if you do the integral for circulation is actually non-zero, which means the origin of the vortex flow actually has vorticity. So it's not rotational. It's not irrotational, sorry. So it's rotational. And that's why when we apply, so exactly at the center of the vortex, we can't apply potential flow theory because we have vorticity there. So it's not irrotational. So that's the key point there to remember. And just here to say, people called capital gamma the strength of the vortex. So just in summary, the equations for psi, phi, and the complex potential for a vortex flow, which is irrotational, should be or could be written in this form like that. Okay. I think these are the key ideas for a vortex flow. So now we've discussed three elementary flows: uniform flow, a source and or sink, and also a vortex flow. So go back now hundreds of years back and think of put yourself in the shoes of mathematicians at that time. They only had these tools to try to describe fluid flow. So they created these hypothetical kind of models for vortex flow, source and sink. Well, uniform flow is not really hypothetical, but it's already there. And they say, okay, from these three main concepts for elementary potential flows, we can actually create more realistic flows. So this is how these building blocks are put together. So this is just a summary for you to look at.